Welcome. The title of today's notes worksheet is Average Rate of Change. And what we will do here initially is talk about rate of change within a context that we are familiar with, and then we will expand that concept talking about it in terms of the title of the notes worksheet, what is called an average rate of change. So why don't we go ahead and dive right in. There's an investigation at the top, and it says rate of change and linear functions. So it says use the graph of y equals 2x minus 1. Pick any 2 points and determine the slope. And if you remember from your previous courses, really slope is the rate that the function changes. So slope is our rate of change. And it says, is this constant for any 2 points on the line? Well, let's go ahead and take a look and try to highlight a couple and kind of go from there. I hope first and foremost everybody is in agreement that the slope of this line is 2. And what that means, of course, is that the line is going up 2, so it's rising 2 every time it runs 1. So let's go ahead and just kind of see that. I put a couple points into the mix here. And of course, that's kind of the idea right there. It's rising 2 and running 1. And that would be the rate that this function changes. As you can see, from here to here, every time we go over 1, we're rising 2. So that is the rate of change, up 2 as it runs 1. And then the question, of course, is it constant for any 2 points on the line? So what do you say we go ahead and just pick another couple points here? I'm just going to try to keep this nice and easy for us. So I'm going to do this point and this point. And if you guys don't mind doing the same there. And the question is the rate of change from here to here the same as it was from here to here? Is it changing in the exact same way? And as you can see, of course, shouldn't come as a great shocker, that it's going up 2 and over 1. And so by definition, on a linear function, the rate of change is constant. And that's denoted in the way we represent this mathematically. Here's our slope right here. Here's our rate of change. What we are going to do here today is expand the notion of rate of change beyond linear functions. So again, just on a linear function, the rate of change is constant. On the graphs of other functions, that's not necessarily the case. And so what we have to do is phrase it differently. And so that's what we're going to talk about here today. Well, let's go ahead and get right into sort of our definition, draw a few things out, get a formula going, and all that good stuff. So here's what I have just in terms of the average rate of change. And so what we want to do is talk about how a function changes for any family of functions, really, quadratics and cubics and quartics and rationals and exponentials and all that stuff. How can we talk about the rate at which a function changes between any 2 points? And essentially it is the slope of the line between any 2 points on the graph of a function. Okay, that looks pretty good. So obviously what we're going to do is kind of sketch one out here and see what that would look like mathematically. All right, so I'm going to go to my next board then as a result. And it looks like there's another investigation here just to get us thinking about it. It says sketch a function, label 2 points, and write a formula for the average rate of change. All right, so let's go for it here. I'm going to just draw a coordinate plane in place, sort of similar to the one I've drawn in a previous lesson. This one will be quite a bit more simplistic, so that'll be good for us. And let's just go ahead and draw, the graph of any function. As long as it passes the vertical line test, I think we're good to go. And if you get a chance here, let's go ahead and just pick any 2 points on the graph of the function. And so what we're looking for here is how does the function change from here to here? And we'll kind of go through that piece in just a second. But basically what we want to do is label those 2 points and then talk about what we would consider the average rate of change. So here's what I'm going to ask us to do. I'm going to keep it relatively simple. Again, easier than the one we saw in a previous lesson where we derived the difference quotient. So if you don't mind that first point right here, sorry I had to put it up here by the way, but this first point we're going to have an input and an output. And I'm just going to call that input A just to keep it easy for us. And as a result, of course, the output would be f of A. If you could put that in just sort of next to that first order pair, that would be great. And then the second point, same thing everyone, if you can go ahead and call it with an input and an output. And again, just for ease purposes here, I'm just going to call the input b, and as a result, the output would be f of b. And what I'm looking for is how the function changes from here to here. And so what we're going to be looking for, everybody, is the slope of this line going through those 2 points. And that's how we defined it up above. Okay, so just in terms of our purposes here, average rate of change is the slope of the line between the 2 points on the graph of the function. And I would ask you this, what would you do to calculate slope here? Well, as we all know, slope is rise over run, or y2 minus y1 over x2 minus x1. So let's go ahead and get our formula going, and I'm going to go ahead and get that y2 minus y1 in place. And then the denominator, of course, would be the run piece. That would be x2 minus x1. And so again, really not too bad. In fact, if you remember your slope formula from previous courses here, this is just a slight extension of that. The only difference is going to be the numerator, as a matter of fact. And the numerator, instead of me giving you the y's, you're going to have to find them. And you'll see that as we go through this process today. But that's our formula. y2 minus y1 over x2 minus x1. Subtract the outputs, subtract the inputs. Wonderful. Let's go ahead and just fill in this piece, and then we'll continue the discussion here. Very simply, it says graphically, the average rate of change represents the slope of this secant line. So a secant line is a line that goes through 2 points on a curve. And we'll kind of talk about that piece as we go through. In this case, you can see it goes through this point, and it goes through this point. There is our secant line. Okay, great. Now, one thing to note, the average rate of change as a definition and as a calculation is fairly broad in scope. Because if I really look at this function, especially just kind of from here to here, you know, the argument can be made that there are an infinite number of things going on between here and here. I mean, the function is going down, it's decreasing, we get a little minimum in here, and then it starts to increase, and then it's gaining steam, and it's increased more and more and more until we get to that second point. So there is a lot going on between these 2 points right here. And so what this slope of the secant line does is it just gives us a broad idea of what's going on from here to here. On average, here is how the function is changing. And that's the idea, on average. Okay, good. Well, let's continue the discussion. So just some examples. Still no number crunching just yet. We'll get to that momentarily here. But let's go ahead and just develop one more conceptual idea before we do that. So example 1, it says, use the graph to determine the consecutive intervals where the average rate of change is either positive or negative or 0. Okay. Well, similar in nature, everyone. If you want, just go ahead and put a coordinate plane in place and just draw a graph looking something like this. And nothing special about these by any means. Just trying to draw a nice continuous graph there that does pass the vertical line test. And let's just go ahead and throw a variety of points up there. And so let's see, let's do this. Okay, right there is what I wanted. And last one right there. Okay, so looks like I have 6 points just randomly placed on the graph of this function. And rather than belaboring the point too much here, all I want you to do is start telling me, without any number crunching or anything like that, talk to me about what do you think would go on with the average rate of change between A and B. Do you think that would be positive or negative or 0? How about from B to C, from C to D, from D to E, and E to F? So let's go ahead and do a couple here and start getting us sort of thinking. Let's go in those consecutive intervals, and then we'll go ahead and place it in either the positive part here or the negative part or the 0 part. Okay, so what do you think? Do you think that the average rate of change from here to here is going to be positive or negative or 0? And if you look at it in detail, the way we've defined the average rate of change, it is the slope of the secant line, the slope of the line that goes through those 2 points. So why don't I go ahead and draw the line that goes through those 2 points, and then maybe we can develop a couple ideas around that. And in this case, if you kind of look at it, my slope, or I should say my line going through those 2 points is inclining. And what, of course, do we know about the slope of any inclining line? It's positive. And so as a result, if the slope of this line is positive, then the average rate of change between those 2 points is positive. So one of the intervals where we would see an average rate of change as being positive is A to B, absolutely. What about B to C? Same deal. Let's go ahead and just draw. Nice and easy, guys. It's all slope today. So there's the line that would go through those 2 points. Do you think the average rate of change between B and C, is it going to be positive or negative or 0? Well, same deal, of course. It looks like that is an inclining line, and so as a result, I'm seeing it has to be a positive value, whatever it may be. Now, here's one more good question before we get to the next interval. What if I asked you which had the greater average rate of change between those 2 intervals? What do you think? Which do you think would be the bigger value, from A to B or from B to C? Okay, and I would say that it's probably going to be from A to B. If you look at just the way I've developed this line right here is steeper than this line right here. The steeper the line, as you've seen before, the greater the slope, the greater the rate of change. And so I would argue that this number, whatever it would be, is going to be larger than this number right here. Greater average rate of change from A to B. Okay, let's continue. C to D. There you go. There's your secant line really going through those 2 points right there. And it looks like it's declining. And so as a result, declining line definitely is going to be a negative average rate of change. This one right here, here's how I meant to draw it, something like that. And what would be the average rate of change from D to E? And in this case, take a look at the line. It's perfectly horizontal. And remember, the slope of a horizontal line is 0, so I'm thinking D to E is in this category right there. And again, average rate of change is said it's a very broad measurement, because if you kind of look at it, all the things that are going on from D to E, you know, it's declining quite a bit, and then it levels off, and we hit a minimum, and then it starts going up again, and it finally hits right here. So even though there are an infinite number of things going on between D and E, what it's saying is on average, the average rate, on average, I should say, the rate of change is 0, because we basically end up where we started. Okay, so again, it's a broad definition. Is it the best? No. But it does give us a general idea of what's going on between 2 points. And then last one, guys, let's go ahead and get E and F. And from E to F, it looks like it's inclining. So I'm thinking it's got to be this. All right, so I hope that's starting to click a little bit here in terms of what we should be looking for. And then obviously what we want is for us to just, for me to be able to give you any function, any interval, and you would be able to tell me on average how is the function changing between those 2 points. Okay, well, let's give it a try. We're going to do what I would consider probably the easiest function to start with, and just some nice basic intervals here, and we'll go from there. So here we go. Find the average rate of change for f of x equals x squared on the following intervals. So I'm going to try to be visual with this one if possible. So if you get a chance, let's go ahead and draw a coordinate plane over there. And no tick marks necessary. I don't think that's required here. But if you can go ahead and just give me the graph of y equals x squared, should look something like that. And what we'll do is kind of manipulate that graph when we do these calculations over here. So one thing to note first and foremost, and I'll leave this to your discretion, but anytime we talk about the average rate of change and it gives these intervals right here, these are going to be domain intervals, x intervals. So I'm going to write that right here, domain intervals. So keep that in mind. The 0 to 1, those are your x's. Those are your inputs. That's the domain values. So from 0 to 1, what's going on? Okay, so let's go ahead and start this out, kind of piece by piece. I think let's look at it graphically first, and then we'll go ahead and do the formula in just a sec. So everybody, when x is 0, I guess that would basically be right here. So everyone put a point right there if you would. And then when x is 1, just move a little over to the right if you get a chance. And then that's perfect right there. And so here's what I'm looking for when all's said and done. Again, I'm a very visual person, so it helps me to kind of see what's going on. But basically, the idea is, on average, how is the function changing from here to here? Obviously, unlike a linear function, it's not constant. So it's not constantly having the same rate of change. But basically, what we're looking for is, on average, what's going on from there to there. Okay, so here we go. Start it out, everyone, if you would. It's just nice and simple. As soon as you see 0 to 1, let's do the run part of our slope. You know that the bottom is going to be 1 minus 0. Okay, so the top is the only issue at hand here. It's the only difference between this and what you've done with slope before. It's y2 minus y1. The only dilemma is I don't know the y2, and I don't know the y1 just yet. All I know, it's the function value when x is 1, and it's the function value when x is 0. That's all I know at this stage. And so again, just watch your notation here. Bottom, again, speaks for itself. But let's go ahead and figure out what f of 1 is. Remember, everybody, this input right here goes into the function. It goes in for x. It replaces the x. And so 1 squared, of course, is just 1. Same thing here, everyone. This is the x value, the input to the function. You put it into the function and get the output. And so just put it in here, guys. Nice and simple. 0 squared is 0. And you could see, obviously, some pretty easy calculations here. And there we go. That's our average rate of change. So it's basically saying, on average, every time we run 1 to the right, it's going up 1. So up 1 over 1 from there to there. Again, on average. Okay. Let's go ahead and get letter B. So now, everybody, this would be from 1 to 3. So here's the 1 right there, by the way. And let's just move over a little bit to the right there, and we'll just call that 3. So just moved over to the right a couple units. And let's go ahead and get that going. So there is that piece. And by the way, actually, just kind of thinking about this, why don't you all put a little A right next to that one, as that was part A. And why don't you go ahead and put a little B next to that one, as that'll be part B. And I guess I would ask a couple questions before we do the calculation here. Number one is, for part B, do you think our average rate of change is going to be positive or negative or 0? And I'm hoping you would agree that it's going to be positive. Also, I would throw another question out there. Do you think the average rate of change from here to here is greater than or less than our average rate of change that we got for part A? And it looks to me, at least, that the slope of this line is going to be steeper than the slope of this line, so greater average rate of change. Well, let's go ahead and do it. Let's calculate it. So here we go. Right away, everyone, as soon as I see 1 to 3, let's do our x2 minus x1 on the bottom. So 3 minus 1 on the bottom. Again, the only difference between this and all the slope problems you've done before is we're not given the y's. I don't know what they are just yet. I have to go out and find them. So let's go do exactly that. This stays. F of 3 means plug 3 into the function. Nice, easy rule right here. 3 squared is 9. And you can kind of see that up here, everyone. Here is 3 comma 9. Looking good. We already did this one. We already put the 1 into the function, and that was just 1. So you get 9 minus 1, 3 minus 1, and that's looking great. And so, again, even though there are an infinite number of things going on between these 2 points, on average, it's going up 4 every time it runs 1. So on average, that's its rate of change between those 2 points. Cool. Let's go do one more here. Looks like I'm going from -2 to 0. So let's see. Here's -2, roughly, give or take, an x value of -2. Here's the x value of 0. It's already in place. And there we go. Average rate of change between those 2 points. This will be our part C. And what do you think right away, everyone? Positive, negative, or 0? It's got to be negative. Absolutely. I have a declining line. And so as a result, it's going to be 0. I'm sorry, it's going to be negative. So let's do x2 minus x1. So just right away, I do 0 minus -2. And then f of 0 minus f of -2. Excellent. Okay, so 0 minus -2 on the bottom. I'll keep that for the moment. F of 0, 0 squared, we already figured out. And then minus f of negative 2. Negative 2 squared is 4. And so that's what I seem to have when I plug those in and get my y values, get my outputs. 0 minus 4 is negative 4. 0 minus negative 2 is positive 2. And you can see that piece right there. So on average, from here to here, the function is decreasing by 2 as it goes over 1. Decreasing by 2 as it goes over 1, on average. Okay, good. Again, it doesn't give the whole story to what's going on between those 2 points, but it is a nice little measurement nonetheless. Okay, well at this stage, really what we're looking for here is any function, any interval, you could tell me the average rate of change. So it would be great if you could pause the video for a moment and check this one out. Pretty comprehensive cubic, just from 2 to 5 there. Could you pull it off? So pause the video for a moment and come on back. Okay, well let's see how you did. So first and foremost, just nice and easy in terms of the calculation. x2 minus x1 on the bottom. Start off with something that you're confident with. That sort of speaks for itself. 2 to 5, so we're going to subtract the x's essentially. So 5 minus 2. The only issue here is that I don't know the y's, and so I'm going to have to plug them in. Now I have this on my paper, and if you get something different, please check the calculation one more time. But I put 5 into each of those values right there. And when I put 5 into each of those values, 2 times 5 cubed minus 15 times 5 squared plus 24 times 5 plus 19, I got 14. And then, of course, I repeated. I took my 2 and I put it in. 2 times 2 cubed minus 15 times 2 squared plus 24 times 2 and plus the 19. When I did that, everybody, I got 23. And so now we have our y's, and of course we had our x's all along, and we're ready to roll. And so let's go ahead and get this. 14 minus 23 should be negative 9. 5 minus 2 is positive 3, and I think there's our average rate of change. So on average, it's going down by 3, so the values are increasing by 3 every time it runs 1. Okay, I'm going to bring my calculator up. I just want to take a quick peek at this one. If you get a chance, you can do the same. So I'm going to go ahead and graph it. Got a moment here, so let's do this. 2x to the third minus 15x squared. You can kind of just watch this if you want. If you want to go ahead and graph it up, that's fine too. Your call. So plus 19. I'm going to go to window here and just try to find a good window for this. Let's see, from 2 to 5. So I'm going to go from negative 2 maybe to 7, just sort of buffer that a little bit. And then I'm going to bring this on up here. Again, you can either follow this or not follow this with your graphing calculator, but just take a peek. And so you get a nice cubic function. Again, look at all that's going on here. I've got an increasing interval, it's got a maximum up here, decreasing interval, a minimum down here, and an increasing upward towards infinity. Again, just an infinite number of things going on as we look at it point by point. And I just want to know on average what's going on between positive 2 and positive 5. So let's go ahead and take a look. Here's x equals 2, so this would be right up here. So by the way, this would be 2 comma, what did we say, 23. And then let's see, 3, 4, 5. So that would be this right here. This, as we said, was 5 comma 14. So you could see, and again, I can't draw on here, but basically I've got a secant line going through those 2 points, kind of like this, hoping everyone sees that. And it is a declining line as we go left to right, and so as a result, slope is going to be negative. And that's exactly what we got. And so what it means, again, is on average, it's going down 3 as it runs 1. All right, good. Let's do a little application piece with this, and then wrap this on up. So I'm going to ask for your assistance on this, for you to do a few of these if you get an opportunity. We'll find out if that's the case. So example 4. A ball is projected vertically upward with an initial velocity of 100 feet per second from 4 feet above ground level. The height in feet, in terms of time in seconds, can be modeled as this right here. And everyone, if you don't mind, Can you box that up for me? Okay. Find the average rate of change on the following intervals. So let's go ahead and take a look at this. I have height in terms of time. Time will be my inputs. Height will be my outputs. And so let's go ahead and see what we have going. I want to know the average rate of change from 1 second to 2 seconds. So again, just picture yourself, the ball is going upward. You start the stopwatch, and as the stopwatch is going, between 1 second and 2 seconds, what is the average rate of change? Okay, well, let's figure it out. First and foremost, as soon as you see from 1 to 2, just a little 2 minus 1 right there. Now, I'm going to do this one time only here. I'm going to go ahead and do, this would be h of 2, by the way, so the height at 2 seconds and the height at 1 second. I'm going to go ahead and do that with my calculator here just to make sure we all get the same values, but please make sure you're doing this as well. And that's what I'm looking for right here. That is my average rate of change on this interval. Okay, so let's go ahead and get those two pieces. Bring this on back. So I have negative 16, and then let's see, times 2 squared plus 100 times 2, and then plus 4. I get that. And so the height at 2 seconds, everybody, is going to be 140 feet. We'll put that in just a second, but while I have the calculator, I might as well do the second one. So let's do that together, everyone. Negative 16 times 1 squared. And then how about a 100 times the 1 and plus the 4. So the height at exactly 1 second, there we go. So the ball is 88 feet above ground at 1 second. All righty, so let's go. 2 minus 1. The height at 2 seconds, not given, we had to find it, and the height was 140 feet. And then the height at 1 second was 88 feet. And if I do this calculation, again, really not too bad. Bottom is 1. Top looks to be 52 is what I'm getting there. And that's it. 52 is our average rate of change. Now, here is what I would ask. As we write that numerical value in, throw some units on that. What do you think? So now we actually have a background, an application for finding the average rate of change. What does this represent here? So it's 52 what? We'll take a look at the top, everyone. What does the top represent? The change in the number of feet, right? 140 and 88. So the top is feet. The bottom, as was given in the problem, is the number of seconds that have passed. And so in this case, I'm seeing this as feet per second. Now here's the key question, just from a conceptual standpoint of what it means to be an average rate of change. Does it mean that the ball is traveling 52 feet per second constantly all the way through that interval? No, absolutely not. What it means is, though, on average, the ball is traveling 52 feet per second on this interval. It doesn't mean it's traveling at that speed all the way through. It just means on average. Okay. Now we're going to do something quite fascinating here. We're actually going to bring that second value in, and we're going to close our interval. So in this case, do you see like 1 second has passed? And in that 1 second, on average, this is how fast the ball was traveling. Now, what I want to know is between 1 and 1.5 seconds. So the interval now is smaller. Only half a second has elapsed. On average, how fast is the ball going? Then we're going to close it even further. Here, only 1/10 of a second has passed. Here, only 100th of a second has passed. And in each case, am I going to be able to find the average speed, essentially? The average velocity is really the better phrase for it. The average rate of change. Well, I'll do one more with you here, and then we'll start to put this together a little bit better. So here's what I'm thinking. 1 to 1.5. So everybody, with speed, give me that denominator. 1.5 minus 1. The only dilemma I see, of course, is top, not necessarily given, although we already found this piece out, didn't we? So we do know the height at 1 second. We found that on the last one. I just need to find the height at 1.5 seconds. So let's bring that up. And I'll do that again. I don't have a problem with that. So negative 16 times 1.5 squared plus 100 times 1.5, and then add that 4. Okay, I've got a 118 when all said and done. So that's good. Here we go. So 118 on top. Remember, the height at 1 second was 88. And then I've got 1.5 over 1. I'm sorry, minus 1. Looks like 30 has passed here. Half a second has elapsed. And when I divide those, on average, the velocity of this ball is 60 feet per second. Okay, that's great. Okay, can I continue? Can I keep making the interval smaller and smaller and smaller? Yeah. Here's what I would ask you to do. Get a little practice just doing this one piece, and then I'll give a couple answers in. Please do letter C before watching me go through. Well, let's see if you did it. And so I've got something along these lines right here on my paper. So I have, again, it's 1.1 minus 1, and then h of 1.1 minus h of 1. You know, in this one, I'll go through it one more time all the way through. So 1.1 minus 1, I think that top left is the only thing that's missing. So why don't I go ahead and get that value, and then we'll go from there. So negative 16 times 1.1 squared plus 100 times 1.1, and then add the 4. And I get 94.64. That sounds great. So here's what I have, 94.64, again, minus the 88. And so let's go ahead and figure out what that is. Again, the bottom, not a big deal. Only a tenth of a second has elapsed. Let's get that value from the top, and I'll do that up here. So 94.64 minus 88, and I get this, about 6.64. Okay, so 6.64 divided by this piece right here, and I'm getting 66.4 feet per second. Okay, good. Everyone all right with that piece? What I'm going to do is close that interval further and further and further. So in that tenth of a second, again, it doesn't say the ball is traveling 66.4 feet per second all the way through that interval. All it's saying is on average, that's how fast the ball is traveling. Okay, how about if only 100th of a second has elapsed? Could you tell me the average rate of change? Well, let's go ahead. I'm going to just give you the answer for this one. If you have it, great. If not, no big deal. So that would be our value down on the bottom. Again, 100th of a second elapsing. And I would need the height there and the height there. At this stage, the hope is you can put these two values into the function. We already have that one, by the way. This one in and figure out what we get. I have on my paper this. So 67.84 feet per second. Okay, interesting. Look at these values, kind of increasing a little bit here. So in that 100th of a second, on average, that's how fast the ball's going. Okay, now take a look. Wow, only 1,000th of a second has elapsed. So a tiny, tiny time interval here. Only 1,000th of a second has elapsed. And what is the average rate of change? Well, let's see. In that 1,000th of a second, so that would be subtracting the two time values, we would find this, of course. An extra one there. Let's go ahead and get that. Minus h of 1. And I have on my paper about 67.984 feet per second. Okay. One more. Now take a look. All the way here. Only 1/10,000th of a second has elapsed. So the ball goes up in the air. Stopwatch starts here and ends just a 1/10,000th of a second later. Could we calculate on average how fast that ball is traveling? And so I will do it one more time right here. 1.0001 minus 1. We would have to find the height at that particular time value. and subtract it from, what did we say, 88 right there, and then divide by this, of course, and I end up getting 67.9984. Now here's sort of the fascinating piece, and this is almost where we transition a little bit to some ideas behind calculus. And so could I theoretically, everybody, could I theoretically keep going? Could I make my time interval smaller and smaller and smaller? So I did 1,000th of a second elapsing here, 1/10,000th of a second elapsing here. Could I do only 1/100,000th of a second elapsing, or 1/1,000,000th of a second elapsing? Yeah, could I keep going and going and going? And could I find out essentially where these numerical values are approaching? And then take a look at the last one. As I close that time interval and I make it infinitely small, smaller and smaller and smaller, could we start to then talk about not what's going on in terms of the average rate of change between two moments in time, but literally how fast the ball is traveling at a single moment in time? And if you look at your answers all the way through your notes worksheet here on this last example, it seems like the average rate of change seems to be approaching a particular number as my time intervals start to get really super small. And what are they approaching? It seems to me to be 68. And so using calculus, and that is one of the things that you start to talk about when you hit a calc class, is not what happens between 2 points on the graph of a function, but what happens at a single point on the graph of a function. And in this case, the application would be, what is the instantaneous velocity? What is the velocity at exactly one moment in time? And in this case, you could be pretty sure that it looks like as that time interval gets smaller and smaller and smaller, it looks like my average rate of change is getting closer and closer and closer to this number right here. Pretty awesome. Really good stuff. I think I'll hold off. I was going to bring up the graph and kind of show this to you, but I think the numerical piece is good enough at this stage. So please kind of look this over, just being able for me to give you any function, any interval, and you can come up with what we would call the average rate of change. Thanks, and please ask questions if you have them.